Okay, we are on day 7 of transformation. Should be honors rotations in your packet. Kind of the same thing we did yesterday, but if you remember yesterday, we only did rotations of 90, 180, and 270. Today we're going to get away from those and do any type of degree rotation. So look at the first example here. We have regular pentagon penta. I want you guys to remember from when we did polygons earlier in the year, regular, all sides congruent, and all angles congruent. Okay. From here, now here's the thing. You look at part A, it says name the image of point E for a 72. Now I don't have a rule for 72. Maybe if you ask me 90, 180, or 270, but not for 72. So I'm asked to start at point E and rotate it 70 degrees around X. All right, well, let's think about this a little bit. As I go from E to P, P to A to T, T to N, and N to E, you guys notice that you go a full 360 degrees all the way around. And how many times did I rotate it? Once, twice, 3, 4, 5 times. All right, and since this is a regular polygon, every time I rotated, it rotated the same amount of degrees. So if I went 360 and I rotated it 5 times, what I can do is take 360, divide it by 5, and you guys will notice, look at this magic number that comes out. Every time I go vertice to vertice, it's a 72-degree rotation. All right, so as I go from E to P, 72, P to A, 72, A to T, 72. So if they just want me to rotate 72 degrees from point E, and since it's positive 72, you guys remember from the notes yesterday, we go in a counterclockwise direction, so that would end up at point P. All right, going on now, 216 degrees. Oh, geez, 216, that's not 72 anymore. But if you take a look, if you take 216 and see if it's divisible by 72, you guys will see that yes, it is divisible by 72. How many times? 3 times. All right, so let me get rid of all the work from the previous problem. And now I'm going from not point E anymore, but the image of point P. So now I'll stay here at P. And now you're going 3 rotations. All right, so 172, 144, and then where do I end up? Right here at point N at 216 degrees. Okay, so it's not that bad. I take 360 and divide it by the number of rotations it takes it to go. All right, so let's apply that to regular octagon. 8's up, pretty clever name, I know. 8 congruent triangles. So again, just like we did for the pentagon up above, I can take 360 and I'll do how many vertices as you count them up? 8 vertices. So that tells me I am going to go 45 degrees every time. All right, so as I go from H to G, that is a 45-degree rotation. All right, so what you guys can do right now, stop the video, see if you can handle numbers 1 through 6 here. Just make sure you're on the correct point. Let me just do number 4 real quick with you before you pause the video and go on your own. 270-degree rotation of EI. Okay, no problem. I have 270, and I know every vertex I go is 45. So that would be, go ahead, 270 divided by 45, 6 rotations. And what you can do is you can just rotate the points. So start with point E. 1, 2, 3, 4, 5. Ends up at G. And then do I. 1, 2, 3, 4, 5, 6. And there you go. You land on HI. Or HG, excuse me, segment HG. Okay, so go ahead, pause the video, see if you can do 1 through 3 and 5 through 6, and then see how your answers matched up. And there are our answers. Some of you guys probably thought 1 and 3. I was trying to pull your leg there with the 3 I's as point I as an answer, but that's the way it ended up. H, G, G, and S, T. All right, so hopefully we're good there. Take 360 divided by the number of vertices they have. All right, next up. Okay, I have an equilateral triangle. I want to rotate it clockwise around the center. Tell me the minimum number of degrees it could be rotated to carry it onto itself. This is something I briefly talked about last week, but we didn't go really hardcore with it. Carry it onto itself. That means I get an equilateral triangle back. So what is the minimum number of degrees I can rotate this triangle and get another equilateral triangle back? So what I did here is I copied this one out, and here's what I'm talking about. So everyone sees our equilateral triangle we started out with. That's not the same one we started with. I got to keep rotating, 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 rotating. Bam! There it is. I get that same one back. Now, how many degrees did that take me? Again, I can keep rotating, 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 rotating. Stop. I get that equilateral triangle back. Now, how many times am I going to have to, or how many degrees can I rotate this so I get that triangle back? All right, well, let's talk. I do this, I go all the way around. Again, I go 360 degrees. And how many times did I rotate it and get that same triangle back? Ready? 1 rotation, 2 times I see it, and then finally we're back 3, back to our original one. So as I go from vertice to vertice, I can take that 360 divided by 3, and that tells me every time I turn this thing from vertice to vertice, I am going 120 degrees. All right, so the minimum amount I can rotate this is 120 degrees. Now, is that the only amount of degrees I can rotate? No. You go vertice to vertice again, that's another 120, so I could possibly do 240 from the beginning. All right, but this did ask for the minimum number of degrees, so 120 is going to be it. Okay, now going off of that, let's say I have a regular hexagon I rotate about its center. Which degree measure will carry the regular hexagon onto itself? So I have, again, 360 all the way around. Hexagon, how many vertices? 6. So every time I go 60 degrees, it will carry it onto itself. We got an issue, though. There's only 4 choices, and 60 is not one of them. But remember what we said. 60 is only the minimum. You go another 60, it'll carry it onto itself again. Any multiple of 60 will carry this hexagon onto itself. So I see 120, that is a choice. We are good to go. All right, so any multiple of 60 would have done it. Okay, again, which transformation will not carry the rectangle onto itself? And we just went over what carry onto itself means, meaning get rectangle ABCD to look exactly how it started. Okay, so everyone sees rectangle ABCD. I need to get one of these 4 choices. We'll get that same rectangle with the A, B, and C in the same exact points. Okay, so a reflection over the line y equals x. Well, let's just take it here right now. Point A, 1, 2, 3, 4, 5, 6, 7, 1. And you guys remember, anybody remember what the rule was for a reflection over the line y equals x? Switch the coordinates. So 7, 1 would go to 1, 7. 1, 1, 2, 3, 4, 5, 6. All right, that point's on there, so we're good to go here. I like it. Let's try point B, which is 8, 9, 1, 2, 3, 9, 3. Let's see, is 3, 9 on there? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it looks That point is 3, 9. That point is 1, 7. So it looks like they switch them here, but if you read the question carefully, it said which one will not carry it over, and we just proved that that one will. All right, how about a reflection of the line y equals negative x plus 10? We got to see what that beast looks like first. So 10's the y-intercept. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the slope is minus 1, so we'll go down 1 over 1, down 1 over 1. All right, and if I draw this in, you will see that if I reflect A, it'll go to B. If I reflect D, it'll go to C. Both points will flip-flop, and I'll still get that same rectangle back. So that will carry it onto itself. So I'm looking for the one that does not. All right, how about a rotation of 180 degrees about 0.66? All right, let's see where 66 is. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right there is 6, 6. Okay, so let's talk. 180 is on the other side. So if you take B and rotate it 180 through that 0.66, you'd end up at C, and C would end up at B. Here's the issue though. You take A, rotate it 180 degrees around that point, it's going to end up somewhere over here. I don't know in that exact point, but it's going to be somewhere opposite. Same thing with D. You take D 180 degrees through, it's going to be somewhere over there. All right, so that's not going to fly. And then if you did choice 4, 5, 5, that which is right in the middle, okay, which I believe is right here is 5, 5, you would see you reflect through, every point would match back up again. All right, so that's why it would be choice 3, rotation of 180 about 0.66. Okay. All right, one more about carrying it on to itself. It's a regular polygon, doesn't tell me what it is, which angle of rotation will carry it on to itself. All right, again, from our work today, I know if I take 360 divided by the number of vertices, 1, 2, 3, 4, 5 vertices, okay, that tells me I am going to go 360 divided by 5. You guys can figure that one out, 72 degrees. Okay, but as you see the choices, 72 is not there. So again, another 72 wouldn't carry it onto itself. So 144, still not a choice. Let's keep grinding. 6, 216. Yeah, buddy. There we go. Okay, so 360 divided by the number of vertices. Last big one we got to do here. Can we rotate we've rotated points, 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 points. Can we rotate a line? So I have this line 2x plus y equals 1. And line M is the image of this line after rotation of 90. What's the new equation? All right, so let's see it on the graph. So let's solve for y here. So everyone subtract over 2x, negative 2x plus 1, down 2 over 1, down 2 over 1. So you guys are going to be reflecting that line 90 degrees. And remember, it's 90, positive 90, so we rotate in a counterclockwise direction. So you guys right now take a hold of your paper, rotate it to the left 1/4 turn, and take a look at that new line for me right now. That new line, we need to come up with the equation of that new line. Right? And I think the easiest way to do it is do slope and y-intercept like we've always done in class. So what I need you to do right now is write down what that point, the new point is for 0, 1, and what's the new point after I rotated for 1, negative 1. Okay, so jot those down. So 0, 1, after you rotated it, should have became negative 1, 0. And 1, negative 1, you guys, you should be looking at 1, 1 after you rotated it. All right, so to find the equation for these 2 points, we do slope, change in y over change in x, so 1 minus 0 over negative 1 minus 1, and 1 minus 0, 1 minus a negative 1. I went in a different order, excuse me. try it from scratch now. Let's go back. Ready? Okay, change in y. 1 minus 0. And now change in x in the same order. 1 minus a negative 1, which becomes plus 1. So the slope is 1/2. And then to find the y-intercept, you guys know the deal. We'll use y equals mx plus b. If you guys don't mind, I'll use negative 1, 0 as my point. 0 equals slope of 1/2. X coordinate is negative 1 plus b. You guys can stop the video, solve for b if you'd like. The y-intercept will be 1/2. So the equation of this line rotated, y equals 1/2 x plus 1/2. Okay, so you notice slope and the y-intercept both change when you rotate a line. And then let's end it on a good note here. You got two triangles, ABC and DEF. We're performing a line reflection and then a translation, all right, to get ABC to XYZ. All right, so again, we had triangle ABC. We performed a reflection over a line and got triangle DEF. And now we're taking DEF and doing a translation to get triangle XYZ. What is our relationship between ABC and XYZ? Well, what do you know about a reflection? Rigid motion, does not change angle measure or line segments. And what do you know about a translation? Also a rigid motion, preserves distance and angle measure. So we did not, ABC and XYZ are still the same looking triangle, just in a different position on the graph. So we know they're congruent to each other. And if they're congruent to each other, they also have to be similar to each other. So these two are congruent and similar. Okay. I'm going to let you guys work on number 5 here, see what you can do on your own. Pause the video again. I'll just circle you when you come back. I'll have the answer circled, and then you can start the assignment for honors rotations. Hope everything's going well, guys. Just not the same teaching in front of an empty class right now.